Alright, this is Fluids Project number 2 with Joseph Brooks and Keegan Usry. First thing you want to do is you start a fluent model, and then we create geometry. I want to make sure our grid and our steps per major are coming up right for what we want. So our graph is looking solid, and we can start what we need to do. Now, you want to draw out a rectangle, like it's already been done, and then dimension it as such using the general dimension. Both the height and the length, which are going to be 0.5 and 1 meter. Then we go into concepts, and we make a surface from the sketch. This gives us our boundary that we're going to be looking at for this entire project. Alright, next we want to open up our mesh settings. Here we can create a mesh and the boundary meshes to make sure we get an accurate analysis of our flow. And this is what your screen should look like. Now, we come in here and we want to first start with our mesh. It'll be a straight set of rectangles where we then face mesh it to give us a more straight lined mesh. Then we add inlet, outlet, top and bottom meshes to further specify what we need. For all these, we want to set our behavior to hard and add about approximately 60 elements per. Make sure our behavior is on hard, 50 divisions, and we want to put a bias for that inlet and outlet so that we can get a better reading on that. And we make sure for our outlet that we're going to reverse that flow and make sure that bias is reversed. You want to make sure you have bias reversed for that outlet flow. Other than that, inlet and outlet should be about the same. And the top and bottom should be irregular hard meshes. Let's see what happens when we don't have the bias reversed and when we do. Here you can look at just how that mesh is coming together and how it gets smaller and smaller as we get towards the edges, giving us a more accurate and more in-depth look at those boundaries, especially at that bottom flat plate, which is where we're going to want to see it. And then for our future steps, after we look at our mesh, we make sure everything's good with our mesh. We're applying it to the right faces or edges. Face meshing should be applied to the whole frontal face. Top and bottom should be applied to the top and bottom edges. And the inlet and outlet should be applied to, respectively, the inlet edge and the outlet edge. We'll go through and look at those. Make sure our bias factors are correct. Should have a bias factor of about 70 for both the left and the right, the inlet and the outlet. There should be no bias on the inlet. There should be one edge with reverse bias on the outlet. Oh, my apologies. There should be no reverse bias on the inlet, just a regular bias, and no bias at all on the top or bottom. Let's see, going through here and seeing what it would look like with and without the mesh, and the parts that it's obsoleting. So let's just see what we're kind of losing as we take away each one of these. Without the outlet mesh, this is what you're left with. And after we add it back in, make sure we apply our geometry to the edge. And we set our type to number of divisions, about 60 divisions. We're going to want to again make sure that number of divisions is 60 and make sure we're not capturing the curvature, and this behavior is going to be hard. We still want to put a bias on it, and we're going to put a bias factor about 70. Again, since we're messing with our outlet, what we're going to want to do is throw that bias in reverse on that edge. Look again at that mesh. See how that's getting more and more accurate as we get to that. Then what we want to do is we want to name our surfaces, our selections. We're going to start with creating a name surface at Airflow. Left click using the face selector, and then right click to create a name solution. And then use the edge selector for that, such as seen here. Create manual selection. So we click on that with the edge selector, we right click, create name selection, and we get that. Make sure we save as we're going along. If the program crashes right now, it'd be pretty devastating for the entire experiment. After we get our mesh set up, we're going to want to look at setup. We wait for that to load and update, and we're originally given this, which gives us an in-depth look at our mesh from this perspective. And here you can see those vectors coming in and vectors going out. You want to check and report quality on this. You can see that down at the bottom, check and report quality. Didn't take long because it's a small mesh. If you have a large object or something big that you're meshing, you're going to have a lot more. You want to go into materials next, and we're going to see air, which is what we're working with. Confirm that these are the values we want to work with, the density and viscosity, which they are. And now that we've confirmed that, we're not going to mess with the solid because we don't have anything aluminum defined. We're going to go into our boundary conditions and look at these named surfaces that we already got from the mesh. So the first thing we're going to do is go into plate. Make sure we're working with a stationary wall and no slip condition. These are the conditions of this project. After we have that confirmed, we're going to want to go into our inlet next. We're going to just maintain that magnitude normal to the boundary with a velocity of 2, which is what we're working with. And that magnitude is normal to the boundary because that is straight across. We're only working with that one velocity changing in the x direction, no y direction. Outlet, we confirm that the backflow reference frame is absolute. That's fine. It automatically organizes the pressure outlet. Then we go to far field pressure. This is where we're going to want to change the type for what this is. Make sure it's on symmetry. It's going to want to go to something else. And we stick with that. With our interior airflow, there shouldn't be anything we need to change. Look at it. It looks good. Next, we can close out everything from setup because we don't need anything more from there. And we can look into our solution. We'll look into our solution category. And first we'll go to methods. Make sure we're on simple methods. Discard the residuals on the right. And we look at the residual. It's going to be set to 1e to the negative 3. We need to make sure that's set to the negative 6. Give us the most accurate result as we can get. And then we're going to initialize that. Go through and make sure we're starting at our x velocity. If you start at x velocity of something different, you're going to get a wonky start to it. And it's better to start it off at the velocity that we're looking at, which is 2 meters per second, with a standard initialization. After we initialize that, we're going to go in and run the calculations. Make sure that number of iterations is set to a high number. It shouldn't hit that number. It should phase out well before that, and you can stop the program, such as I did. But we want that number to be high so that it keeps going until it stops. We can see more of what we need from skin friction by making sure we're on all of our wall fluxes and we're looking at our skin friction coefficient on that plate. That's our important part for both wall shear and the skin friction. This is the same process, going through a wall flux, a wall shear, and then we want to choose our direction vector for our X. And we have our two XY plots that we're wanting to develop. We have our skin friction and our wall shear stress, which we'll see here in a second. Here's our skin friction coefficient. And then this is our wall shear stress. You can see both have that cubic nature to them, as expected. After we finish setup, we're going to want to look deeper and go in our solution. Now this will let us chart out what we really need to do. Now first we want to make sure that we have a contour and a contour plot. About symmetry 2, which is the entire geometry of the whole feature. We're looking at our global range, taking everything into consideration. And this is what we get for a velocity contour plot. You can see that velocity gradient changing over there. In a second, we'll look at what our vectors are looking like. For now, you can see that velocity contour right there as we get closer and closer to that boundary layer. And then you can see when we add in the vectors, what our vectors are looking like as we get closer and closer to that boundary layer. Very similar to how our velocity plot was looking. This contour plot we added in all domains, symmetry, and we can change this to show our pressure. We can see our pressure contour plot right here with our pressure contour and the key on the left and on the right. Then I want to look at our charts 1 and 2. And to get those charts, we have to add in lines that are giving us our velocities at certain points. So our first line is we're going to be looking at 0.35 meters. And we're going to put that original point at 0.350 and the second point at 0.35.5. The same for 0.75. So it can take us all the way across that feature and we can really see that growth. After we add our lines in, we can reference them in the charts. For our velocity chart, for 0.35 is what we're looking at right now. And set a title for velocity, put our series to 1, and adjust the variables as shown. For our second velocity chart at 0.75 meters, we're going to look at line 2, series 1, where we're going to change our variable to be representative of what we want to see in our data. And if we take a look back here, once more at our contour plot, take a good look at that and see just how that's looking. And those would be the final results of Project 2 with Fluent.